Okay. Hello, everyone. I guess this is a very special lecture. This is the first lecture on this channel where I have an esteemed guest. This is my friend he's currently a graduate student from U Toronto, and he's doing research on quantum information. And we met each other at a scholarship event maybe 1 year ago. And Simba has been very, very nice to me. He's been showing me all around um, my current institution because he used to go there for his alma mater and during his undergraduate degree. And I want to stress that science is a collaborative effort. And the more friends you have, the more things that you can learn. So with no further ado, I will pass the mic to Simba. Simba, can you hear
Thank
me?
you. Yes, I can.
All right, good. So here you go.
So thank you, Leaf. I also met Leaf like in a scholarship event like a year ago, and he's a very nice guy, very brilliant. Just from his videos, you may found it on channel. Like he's like genius in most field of physics, but I'm not. I'm not as smart as him. So I'm probably only like a specialist in quantum information, and I have partial knowledge about black holes and stuff. And also I'm very interested in computer science aspect as well. So if you guys are interested, I can also do a series on computational complexity or NP completeness and stuff. Yes. So those are like things. Cool. So I really like the idea of the polyphysics projects that Leaf proposed, and as addressed from one of my very respected professor, also like where I think is like also Lee's very respected professor at Hong Kong U, Dr. Lee. Is that like if you want to understand something, then the great thing is to like teach something. So that's why I'm like teaching quantum information and computation. Yes. So without further ado, let's get started. Okay. So first of all, let me do some self-introduction. So hello, my name is Xiang, or you can call me Simba. I'm from Hong Kong, and currently, so I did my Bachelor of Science in the University of Hong Kong. So basically, Leeds current institution, and I did a major in physics intensive and a minor in computer science. And I'm currently a PhD candidate at the University of Toronto, Canada. So I'm currently in Canada, and my research interest in quantum optics and quantum information. So I think one of my proposed topic now is to use all-photonic quantum computation. If we have time, I could probably talk about it at the end of the series. So that would be probably like 3 months from now. So yeah, so basically this is a bit about me. Cool. So without like hesitating, let's go into the topics that we will cover in this series. So I just want to stress that quantum information and computation, basically they can summarize as quantum information science, is a very huge topic. And I'm not familiarized with all the topic in this field, of course. So I would choose a topic that I find interesting, meaningful, and most likely that I'm familiarized, and I wouldn't make a fatal mistake, and I can convey the meaning correctly. So yes, so I gained the insights from the lecture notes from Dr. William Wang at Hong Kong U, which is when I learned the course, and also Professor H.K. Low, which is currently my research supervisor, my PhD supervisor from the University of Toronto. Cool. So their lecture note is pretty cool. And okay, and for the majority of this lecture series, I will follow large guys. Cool. So what are you expecting from this lecture series? So this lecture series is made for students with an interest in grasping an overall view in the field of quantum information science. So you should expect to learn some basic quantum mechanics and information science, and also the mathematical foundation. And also you could expect the basic knowledge in quantum information science, both theoretical and practical, like both in computation and information. And also the potential application. It's not potential, it's actually the application of quantum information science, because we are using quantum information science like quantum communication for a while already. So I think it's already like at least 10 years, it's probably 20 years already. Yeah. So part of this course assumes basic knowledge of undergraduate mathematics, basically second year like vector space and also quantum mechanics. If you're not familiarized with those, don't worry, you can still watch the series, because like I think I will go through them in the series. And also like you can watch Leaf's video. So he did a very good thing on like quantum mechanics, like the mathematical foundation. Cool. So before we start, I just want to make a disclaimer that I'm only a first-year PhD candidate. And of course, I have limited knowledge and ability. So if you found anything on my lecture slides or that I'm talk is wrong, please not hesitate to let me know in the comments, and I will correct them as soon as possible. And also, this lecture series does not aim to give you a complete knowledge in QIS. If that is my aim, then probably it would take like 200 hours. And of course, like you wouldn't have time to watch. I wouldn't have time to record. Yes, so therefore I'll only go through some parts. So I would go through the main ideas slowly, but some parts will go through them very quickly, including the detailed proofs. But if you're interested, I will point you possible sources that you can find a proof. And also, like, if many people are interested, I can go through them in the lecture series as well. So yeah, it's basically a very open like course. Cool. So about the references for quantum information science, let me show you. My personal favorite is the Nelson and Trump, which is a very classic one. Just let me show you. It's this book. If you're doing anything about quantum computation and quantum information, you will see this book. It's in 2010, and it has a very good like introduction to the overview, like the fundamental concept, the mathematics, computer science part, like the quantum computation and quantum information. So you got everything in a nice and tidy way. But the bad thing about this book is like I found it a bit too like rough, in a sense, like it doesn't go through the proofs doesn't go through the math very detailedly. So you can see there's only like 600 pages. So that's not a short book. So it's but from this book, you should expect to get the overview. If you're a more mathematical person, I recommend this book, which is much longer, first of all, and also it go through some of the parts very detailedly, and like the math very nice, including the whole levels bound, like the bounds we'll talk about it in the later course, and also like a lot of lemma. So this book is for mathematical students. I will use part of the book to do the proofs, but for the purpose of the whole course, I mainly focus on the first one. Yeah, and the third book is called The Theory of Quantum Information. This is the textbook of the quantum information course from the CS department in University of Toronto. I personally didn't read it. I just like have a browse of the topic, and I think this book is open source, so you can download it online for free. Just found it similar. The content should be similar to the first one, the Nelson and Trump. So for the purpose, I would just follow Nelson and Trump. But if you're interested, you can download it and read it. Yes, that would be great. Cool. So let me get back to the slides. Cool. So nice. So the topic in this series that we will cover, first of all, in this lecture, I will give you a background of quantum information science, like the development and the review of linear algebra. And in the next lecture, I will tell you a basic or essential quantum mechanics for quantum information. So we will not go through like the classic quantum mechanics lecture, like helium atom, hydrogen atom, like the perturbation theory. Those we will not do that. So we basically do essential quantum mechanics for quantum information. Then we'll go into quantum computation, which includes topics like quantum circuits, quantum gates, quantum Fourier transform, and quantum search algorithm. And I would like to talk about the Shor's algorithm. Yes, that's like the first time we have the quantum supremacy. And then in the next section, we'll have the quantum information, where we talk about more like an information science course, including distance measurements in classical and quantum information, and also very important thing, the quantum error correction. So if you allow me to talk like a story about it, I learned it from my previous supervisor, Professor Hoifeng Chow at Hong Kong U, very genius professor. So like he said, like 30 years ago, a lot of people just found like quantum computation is like a story. It's like a fantasy. Wow, in theory you can do whatever, but like in reality, you couldn't do anything. because of quantum error correction. In classical computation, error correction is very important, but back in 30 years, nobody thinks like you can do error correction in quantum, because whenever you're doing anything, you're doing measurements and you break the quantum system. But I think it's like some guy in quantum error correction, I couldn't remember the name. Is it like Shor's? Probably. It's like either Peter Shor or like someone else did like quantum error correction idea, and then suddenly people realize, oh, we can actually do error correction in quantum information science, and then that brings the whole field to like vibrant life. So very important quantum error correction, and also we do entropy information, basically like the classic topics. And then we'll do applications, including quantum key distribution and like different formulation of quantum computers. Yeah, so this is a topic in this series. Cool. So probably let's get started. In the first part, I will talk about the background of quantum information science. So quantum information processing is using quantum mechanical effects in computational field. That include the theory of computation, cryptography, information theory, error correction, privacy amplification, communication, and there's also something called the quantum internet or quantum networking. It's a very grand field as well. So by doing so, we have many great applications which will revolutionize the computation and information transfer. So about information transfer, the best thing is like by using quantum information transfer, you can make everything safe, theoretically preventing the third-party eavesdropper. That's by quantum key distribution. We will talk about probably 3 months from now. For quantum computation, it can solve some problem much faster than the classical computer, which is the including like one of the complexity subclass of the polynomial complexity hierarchy. So it cannot solve the NP-complete problem with a polynomial time algorithm, but it can solve certain like complexity subclass problem. So I will talk about it later in like the lecture that we are focusing on quantum algorithm. So for example, let me just give a quick example, the prime factorization. So normally when you're watching this video on YouTube, or when you're sending WhatsApp to your friends, every information is encrypted by currently it's by a way called the RSA. So the RSA cryptography method is basically used the computational complexity of a large prime number factorization to do the to protect your information. So basically, 3 times 5 equals to 15. That's easy. But if you want to find what is 15 made of, it's very hard. Like generally, if you have a large number, then this could become very, very difficult. So with a classical computer, you can compute it for a long time. That means like with current technology of like the bad guy who like to steal information, he did not have the power to compute the prime factorization of a very large number, so which protects your information security. However, so this is the RSA idea. So they will use a very large compound number multiplied by 2 very large prime number as a public key, and only you or only Google or only YouTube or only WhatsApp, Facebook, Mark Zuckerberg knows the private key, like knows like what are the prime numbers. So they can use a private key to unlock the information. But the private key is not known by other parties. So if you want to find the private key, you have to try every possible factors. For example, you need to start trying 1, whether 1 is a factor. Yeah, 1 is of course a factor. You should try 2, whether 2 is a factor. No. 3, no. 4, no. You want to try 4. But 5, no. 7, no. 11. You should try every prime number. That would take a huge amount of time. And then it protects your information security. But in quantum computer, we have a much more efficient algorithm called the Shor's algorithm, which I will talk about it later. It uses a quantum idea, and it makes the whole thing a lot faster, and it makes the whole thing like doable. And basically, if we have a good quantum computer, then all the cryptography method, not all, like the majority of the cryptography method we're using currently will be dead. So that's why we need to study quantum information. Of course, there's like other proposals, and yeah, we'll talk about it later if we have time. Cool. And also, like, I just want to let you know that quantum information science is a very fast-growing field. Europeans and the Americans are spending billions on quantum computing research. And just let me just tell you, like, in the University of Toronto, or before I came, I only know that Professor Lowe is doing quantum information research, but currently they're hiring another professor doing quantum information, and also they have an open vacancy for that. So you see like how vibrant the field is. And also like big companies like Google, Intel, IBM, they're announcing better and better quantum computers progressively. So the latest news I remember is from Google or something. They did a quantum error correction, like the surface code on a 5x5 or something. I forgot. Like, so you see, like even the very great companies are doing research, and there's also other quantum information company like IonQ or Quantum Bridge, and they're also doing research. And including China. China's building a national laboratory for quantum information science. And all the big countries like China, USA, I don't know whether Europe has it, have constructed a quantum backbones for safe communications using the quantum key distribution idea. And also they have like satellites for quantum key distribution as well. Yes, basically with decoy state achieved, and the decoy state idea is proposed by, partially proposed by Professor Lowe. So we'll talk about it probably 3 months from now. And so you can see like the field is growing very fast. So it's very excited that I got a chance to have a lecture series on the fast growing field to let you like know what is going on right now. So let's start the essential math, to overview of the essential math. So I will assume the viewer of this lecture knows the undergraduate level second year equivalent mathematics. Basically, we need this linear algebra, including vectors, matrix, tensor, and yes, I will recap them quickly. Don't panic. And also in this series, we will adapt a physicist's point of view. So I'm not like Leaf. Leaf is still here. Like he considered himself as a mathematician, but I consider myself as a physicist and probably an engineer. So like I'm not as good as him. So it's basically I would talk about math pretty quickly. I would not go through the very rigorous definitions, and yeah, and basically I would just grasp the idea. Partially because I am not able, my ability does not allow me to do that. Cool. So vectors, I'm sure all of you know what vectors is. You learned it from high school. But in a more mathematical sense, you could define vector as a member of vector space. So like everything could be a vector in a sense, like a polynomial can be a vector if you have chosen a vector space, right? But let's not talk about that. So vectors are member of vector space, and the vector space fulfills 8 definitions. We'll go through them in 10 seconds. So in quantum information, in your everyday life or probably other field of physics, how do you write vectors? Basically write X with a arrow on top, or probably write X with a lower underscore. But in quantum information science, it's not generally applied to physics, but it's only in quantum information science. We use vectors like cat. So we write a bar, a V, and then I don't know what that called, but like we call it a cat. And the dual vector of cat V is called a bra, which lives in the dual space. You can simply think of it as so the cat is like a column vector, and bra is like a row vector with the Hermitian transpose. So you transpose it, and also you did what is it called? The complex conjugate, right? So this is a bra. Yes. Cool. So the definition of vector space, there's 8 definitions. A vector space V over field F, which that may have 3 vectors from V. That we have any 3 vectors from V, like U, V, W, and any 2 real numbers A and B fulfills the following properties. The first one is the commutativity. Basically, U plus V equals to V plus U, like cat U plus cat V equals to cat V plus cat U. So they must be the addition. So basically, the 8 properties are the properties for vector addition and scalar multiplications. at this moment, we did not define the scalar multiplications. The vector multiplications. So maybe from high school, you learned like we have dot product, we have cross product. But for the definition of vector field, we did not need that. We did not define the vector multiplications ways. Right. So there's 4 for vector addition. First of all, they need to be commutative. Also, they need to be associative, just like what I have written here. Do I have like a can I have maybe I will talk about try next time. Yeah, and also they need to be distributive of a scalar multiplication with respect to the field addition. So basically, if you multiply a in front, it should be following something like this. And also the the distributive of scalar multiplication with respect to the vector addition, basically like that. Oh, sorry. That's why I found maybe this. Sorry. Yes, sorry, my bad. That is I skipped two. I skipped the slides. We are talking about the scalar addition. Sorry, the vector addition. After associativity, you have the existence of additional identity, which is the existence of 0, such that a cat u plus cat 0 is still equals to cat u. And also you need to have an additional inverse, which for any cat u, there is a cat x, whatever the x is, where u plus x equals to 0. And then we denote x by the minus u, negative u. Yes, these are the 4 properties for vector addition. And for scalar multiplication, there's also 4. Yes, there's also 4. First of all is the compatibility of scalar multiplication. The existence of scalar multiplication identity elements is basically 1 in most cases. And just as I mentioned, the distributivity of the scalar addition, scalar multiplication with addition of scalar or addition of vectors. Yes, basically like that. So if a space fulfills these 8 properties, we can call it a vector space. And in a vector space, depending on its dimension, we can have an orthonormal basis, or we can have bases. Basically, the bases are something that you can express any vector in this vector space by a combination of the basis vectors. So by a combination of basis vector with different like coefficient in front. But in physics, we are more interested in considering the orthonormal basis. So orthonormal basis of, did I talk about Hilbert space as well? Okay, I'll probably talk about later. Yeah, of the Hilbert space H is like we have the following properties. First of all, the n here is the dimension of the vector space. So for any two orthonormal bases in the vector space, if they're not the same, then their inner product should be 0. Did I define inner product later? Yes, I did. I should put this slide later. I will talk about inner products. Their inner product, or you can think of it like as your like dot product in your high school, is 0. And also, for any vector in the Hilbert space or in the vector space, it can be written as it can be decomposed into components. So it can be decomposed to some vector, some number times some like scalar number times the vector basis with a summation, like for all the vector bases, like the basis vectors, like the orthonormal basis vectors. And also like for any vectors in the Hilbert space, we can denote the squared norm as something like it, and we'll define the norm later. I think this slide should come later, but I know why I put it here. I'm so sorry. And yes, so or if the vector if the dot product or the inner product of the vector with any basis vector is 0, we can only have the vector is 0. And also, yes, also like the vector basis should span through the whole Hilbert space. This is the definition of basis, orthonormal basis. So I will talk, let's talk about linear operators. So a linear operator is actually a function between vector space V and W. So it's basically mapping something from vector space V to another vector space W. But of course, they can be the same. So basically, it's like the definition is like here. If A is a function, then it will act on every single basis vector of the vector space and make it to another basis vector. This is a linear operator. So essentially, we can take it as a linear operator. We act on each basis vector, and later on, we will see how we apply operators on quantum system that will change the quantum states. We'll talk about it in just a minute. Yes. And here comes the definition for inner products. The inner product is, actually, I should talk about it earlier. So an inner product is a function which takes the input from two vectors from a vector space and produce a complex number. So the definition is like an inner product. It's basically a function of two, takes on two vectors from a vector space, give you a complex number, which have the following properties. The first one is the function is linear in the second argument, basically something like this. So yes, and also the inner product must be commutative with dagger side, with like complex conjugate. Yes, so like the second property. And the third property is like inner product of itself must be greater than or equal to 0, or we can call it postulate, semi-postulate definite, with equality only if the vector is 0. So later we will write the inner product in quantum mechanics as this, something like this. So a bra and a cat. So that's why we call it a bra and a cat. So you can see a bracket, right? Pretty nice. A joke from, it's a joke from Fermi. I forgot. Like it's a joke from like a previous physicist, and he just found it funny, like called it bra and cat. But like now we are all using it, so it's pretty cool. Cool. And Hilbert space. I should define Hilbert space earlier. So a Hilbert space is a complete normed vector space which fulfills two requirements. The first one, the norm is well-defined. So we have a well-defined norm, just as we mentioned before. You can define it as this way. And also, the vector space is complete, where every Cauchy sequence converges. We'll not go into detail. Probably Leave will go into detail in the series. Yeah, here we're going to detail in the series. So basically, Cauchy series is a series when you're like doing a ball and the ball is like small enough, and then whether the number is still in the vector space or something. If this converges, then it's good. Then we can call it a Hilbert space. And many of the quantum mechanical systems live in the Hilbert space for different dimensions. So if you're not a mathematical person, you can just take Hilbert space as vector space. Yeah, Hilbert space is a vector space, but with some of more like thing. Yes, so you can just think of it as vector space without caring all the details. Cool. And Hermitian matrix and operators. So as we mentioned about operators before, but in physics, we are more interested in Hermitian operators or Hermitian matrix. This is for a reason. First of all, let's go through the definition. Square matrix that is said to be Hermitian matrix if it is equal to its conjugate transpose matrix. So you know, like the conjugate is basically changing A plus BI to A minus BI, and you transpose it. So if a matrix equals to its conjugate transpose, then we call it a Hermitian matrix. So Hermitian matrices have two very important property in quantum mechanics or in the study of physics. The first one is the eigenvalue of the Hermitian matrix are real numbers. So you see this is important because real numbers can represent physical quantities, like real physical quantities, including like energy, including spin, including like angular momentum. So see, like real number is very important. And Hermitian matrix also have orthogonal eigenvectors for different eigenstates. Sorry, different eigenvectors for different eigenvalues. So they so basically the eigenstates are all linearly independent, of course, and also they're like orthogonal to each other, which is very good. And the proof is not hard. If you're interested, you can like it's left as an exercise, or you can find it in any textbook of quantum mechanics. Yes. So why we say like Hermitian matrix is important is because of the second postulate of quantum mechanics. We'll talk about it in the next course as well, but let me just give you a brief overview. So for every observable properties of a system, including energy, including angular momentum, including location in space, including like momentum, including everything in quantum mechanics, are what we call an observable property of the system, and there is a corresponding quantum mechanical operator that is corresponding to this observable number. So this is often referred to the correspondence principle. So basically, if you have a system and the quantum system is represented by the cat, and when you would like to get some information from the system, for example, we would like to get the energy of the system, you basically just act a Hermitian matrix corresponding to the energy thing on this system, then you can get the energy and the state afterwards. So this is what we call the correspondence principle, and the energy operator is what we call the Hamiltonian operator, right? So basically, after making an observation in a quantum system, you have some probability of getting any result. Is any result from the the probability of getting any result is calculated using the squared probability density. And also, the possible observation results are the possible eigenvalues of the observables. So the observable is a Hermitian matrix, and basically any possible results is the possible eigenvalues of that matrix. So that you know why we want the eigenvalues to be real, because they represent real physical quantities. And also, the state of the system after the measurement collapses to the eigenstate corresponding to the eigenvalue you obtained from the measurement. So this is basically how quantum mechanics works. And we'll talk about it more in next chapter. This is only give you like an overview. And also we have the simultaneous diagonalization theorem, which is also very important. So suppose A and B are two Hermitian operators. Sorry, I should talk about commutator and anti-commutator first. So we can define a commutator between two operators A and B. So basically, the commutator between A and B is AB minus BA. So because you know, like matrix multiplication is not commute generally. So AB in general does not equal to BA, which means the commutator between A and B does not equal to 0 in general. But if they turns out to be equals to 0, then we can have AB equals to BA. Then we say A commutes with B. In a sense, like you apply A first or you apply B first, doesn't matter, which is a very good thing. Similarly, we can define the anti-commutator, which is less likely to be used to be a great bracket AB, which is equal to AB plus BA. So if AB plus BA equals to 0, we say the A is anti-commute with B. So with the knowledge of commutator, we can have a look of the simultaneous diagonalization theorem. So suppose A and B are Hermitian operators, and if AB equals to 0, sorry, then AB equals to 0, the commutator of AB equals to 0, if and only if there exists an orthonormal basis, such as both A and B are diagonal with respect to this basis. In a sense, you can find a set of eigenstates where it is both an eigenstate of A and an eigenstate of B, so that we say A and B are simultaneously diagonalizable in this case. Why this is very important? This theory is very important. It means like if two observable commutes, then we should be able to find a set of eigenstate that suits both of them. So I will demonstrate why it is so important. So imagine that you have a quantum system like electron, whatever, and you want to find the energy of the system corresponding to the energy of the system. And this is by doing a Hamiltonian operator on the cat of the system. So, but only using one quantum number couldn't be enough to describe the whole system, right? So if you have another operator that commutes with the Hamiltonian operator, for example, the spin or the angular momentum operator commutes with the energy operators. So angular momentum operator commutes with Hamiltonian operator, then you can act anything on it. So basically, you can find the system's angular momentum without disturbing the system energy. And that is a good thing, right? Because like if you disturb the system energy, then you're not describing the system, but you're destroying the system or you're changing the system. So that means then So like, for example, the angular momentum operator does not affect the energy eigenstates. And then we call them good quantum numbers in a quantum mechanics point of view, like in a hydrogen atom point of view. So if you know, in hydrogen atom, we have the principal quantum number, which is n. That is to specify the energy. But for the same energy, you have degeneracy, right? Because probably you have many states have the same energy, and you want to distinguish those states, and you need to use like the spin quantum number and the spin magnetic quantum number, like NL and NL, and most likely you need to use like spin as well. So it's basically those operators are all commute with each other. Then when you're like using those numbers, so then we can use it as a good quantum number. Otherwise, there will if any operator will change the result of other operator, then the sequence of doing measurement will be important, and that is not what we want, because we want to describe the system without affecting the system at all. So this is basically why the simultaneous diagonalization theorem is important. Yes, basically. And last but not least, the tensor product. A tensor product is a way to put vector space together to form a larger vector space. And this construction is crucial to understand the quantum mechanics in multi-particle system, especially in quantum information. Imagine you have one electron. It can be either spin up or spin down. Then it lives in a two-dimensional vector space. But if you have two electrons, it probably the collective lives in a four-dimensional vector space, and we will talk about it in the next slides. So let me first give you a definition of tensor product. It might not be a definition, but like a realization of tensor product. So suppose V and W are vector spaces of dimension m and n, respectively. So for convenience, we also suppose that V and W are Hilbert spaces. So then the tensor product between the two vector space V cross W is an nm dimensional vector space. And so, for example, if I and J are orthonormal bases for space V and W respectively, then the tensor product between I and J is a basis for V cross V tensor product W. Yes, so this is the definition. If you don't know what I'm saying, that's fine. We'll go through an example in the next page. So we often use the abbreviated notation, because drawing the O cross is like O times, it's like very complicated. And you know, physicists are very lazy. We don't want to type that much. We don't want to write that much. So we use a very simple notation, either write it in sequence, or even just like write VW in the same cat. That represent the same thing, and with a much shorter with a much shorter representation. So the example of tensor products, just what I mentioned. If you imagine you have many electrons that can be either spinning up or spinning down. So let's denote spin up by arrow pointing up and spin down by arrow pointing down. So one electron lives in a two-dimensional vector space, right? So the two bases of this vector space is basically up and down. So any state of the electron can be written as a constant number up plus a constant number down with a proper normalization. But if you have two electrons, and the two electrons should collectively form a four-dimensional vector space, because there's four possible basis vectors. Like if both spins up, the first spins up, the second spins down, the first spins down, the second spins up, and both spins down. There are the four there are the four basis vectors, and it is very important, the four basis vectors. And we'll define what we call a Bell pair, or a Bell state, or an EPR pair in the next chapter, based on that. So two electrons collectively form a four-dimensional vector space. What about three electrons? Three electrons collectively form a vector space of 8 dimensions. If you can try to write a set of basis vectors, I'll give you probably 10 seconds. You can pause the video here. So the answer is up, 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 down, up, down, up, down, 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 up, down, 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 up, and down, down, down. Yes, there's 8 possible basis vectors. So yeah, you got the point. This is why we need tensor products, because maybe we have two distinct or two two non-related vector space. for two different electrons, but we want to put them in a large system, we need to use tensor product. Yes, basically that is. And commutator, we talk about it. Cool. And that's the end of the first lecture. I'm sorry for like messing the things up and down. And it's the first time I do lectures in this series. I hope you like it. And if I did anything wrong, please let me know. And yes, I'm sorry for, I'll do more preparation next time. Yes. So for the next lecture, we'll go through the postulates of quantum mechanics and the basic notion in quantum information, including qubits, the Bell state or EPR pair, and other related topics. And then, yeah, I will probably see you in the next lecture. Yes, Alif, do you have any last minute like?
Yeah. I would like to say two things. I want to say, Simba, I'm very impressed by the lecture. It is very, very good. You outline the physics very, very well. I do have some very minor questions if you don't mind. It's very basic. I'm sure that you can answer it, so don't worry.
Yeah.
The first question I have is regarding Shor's algorithm, right? When you talked about it, but I know you haven't actually talked about it in detail. But to my knowledge, I know that Shor's algorithm is used to factor large numbers, right? Prime factors of large numbers, right? And they do it using FFT, and it you will talk about that later. But my question is there any case where Shor's algorithm is worse than the standard algorithm? Or because yes.
That's a good question. I think so. If you're factorizing like
small numbers, right?
15, like
yeah,
15, for example, 3 times 5, then probably just by trying like
it's faster to do it like that, because doing Fourier transform would be more difficult. I see. Okay, that's a good. I have one more question. You probably don't know this because you're a theorist, and the question I have is a little bit because can you go back 2 slides or 1 slide?
Go up 1 slide.
Yes.
Yes.
Maybe 1 more. Yeah. I think we talked about this in a lunch discussion.
Yeah.
You told me that it is quite easy to generate pairs of entangled states. So this, I'm not sure. I'm not sure if Simba mentioned explicitly what entanglement is, but the tensor product between two states is basically the whether if you can write it as a tensor product. If you can't write it as a tensor product, is an entangled state, correct? I think.
Yes.
Okay. So you probably don't know the answer, but because you're a theorist, why is it so difficult to entangle 3 pairs of states? Because 2, as you say, 2 is very, very easy. But 3 is very, very difficult. So I'm not expecting you to know the answer, but I don't know the answer. So
I do got the answer. I don't know whether it's like the best answer I can give, but
it's all right. It's all right. I mean, it's a really out of the blue question, so it's fine.
Exactly. So in the quantum mechanics lecture you have done, or probably in the quantum mechanics thing you have done in your high school and your not high school but in your university, you always talk about like the entanglement between like 2 electrons or 2 photons or something, but actually we can have entangled photon and electrons. So for example, we excite an electron and we let the excited electron to go back to the ground state, and it will emit a photon. And the photon, depending on the electron spin, the photon will have a either a right chiral polarization or left chiral polarization. That's the way you can you can entangle an electron and a photon. Generating it is easy, but if you want to do the entanglement later on, it's very hard. We can do like, for example, 2 photon entangle with each other. That is easy because we can just generate 2. But if you want to entangle 2 photon, I think you can do it by using quantum circuits. I am not sure how to do it. I think, but if you want to entangle a photon with an electron, that would be generally hard. Yeah, that's the first thing. And why it is hard to generate 3 is because of the coherence time. I think so. Currently, if we have a trap ion, so this is a realization of qubits. So how do you realize qubits in your daily life? The first idea is like trap ion. So basically electrons on a very large. Yeah, I discussed actually yesterday with a new professor here called, I think it's Boris. is a new professor in solid state physics, doing condensed matter for quantum computation, and he told me like the thing is basically you can have a atom with probably 100 proton, and then the like outermost shell electron is very loosely bounded to the atom, right? So that electron you can easily entangle it with another atom with like 100 protons or something.
I see.
So
Okay.
yeah, and the thing is like establishing entanglement is easy, but keeping entanglement is hard. Typically for the electron, because it is like actively interactive with the universe, right? So actively interact with the universe, then any disturbation, for example, like if there's a hydrogen atom collide with that atom, then the entanglement will just lose because the process is irreversible. So using trap ion or using like this kind of realization would be very hard because the we call it a decoherence time. The decoherence time scale is very short. And the second realization is using photon, which is what I'm currently working on. The photon is good because you can just like create two entangled photon or three entangled photon and put it in a fiber, and like the fiber just like go 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 go, and this would be great. It can keep up to like milliseconds. I think it's like much longer. But the bad thing is like it's only for information transfer. You cannot do like you cannot currently do quantum computation with it, because doing quantum computation you need to have the photon interacting with like some of the matter, with some of the like matter qubit, like the atom with a very large like atomic number. So these are the two things that are difficult. And so what I'm currently working on for my PhD most likely is to do all photonic quantum computation. So they're proposing you do not need to use like a photon interacting with like a large atom, but you're just using a chain of like entangled photon, and then you can do quantum computation. Currently I do not know how to do. Probably I know like in 2 years time that I can come back to give a lecture, and yeah, and I think that's the answer.
Thank you so much. So in short, it's theoretically very easy, but in principle, very, very difficult. In practice, very, very difficult. Okay,
Yeah,
that's
so
very good.
you see like most of the quantum information science, or like most of the thing as we talk about in the lecture series, like here, it's like for quantum information science part, it's all talking about realization, although it's
I
theory,
see.
but theory for practice.
I see.
So
That's
like,
good. That's good. Yeah, I mean,
yes,
yeah.
right.
I do have a minor, not really a comment, but it's just to let the viewers know. Simba in one of his slides he used ket 0 as the zero vector, but in my lectures I use ket 0 as the up vector, the up one.
Oh right, yes,
yeah, yeah.
I'll
I mean,
use that later. Yeah, right.
no, I mean, yeah, it doesn't matter. It's just a matter of notation, but it's just it's just I've observed that when Simba defined the vectors. Actually, the funny thing is uh, you claim when you're praising me, saying that the mathematics, this definition of a vector space is actually better than the one that I gave a week, maybe a day ago,
Yeah, this
because
is like what I learned from lectures.
my one is not very good, because the thing is I said that you could just add vectors and their linear combinations yielding the trivial solution. It's not a really good definition. This one's much better, because what's nice is this one is actually related to a group, so it's essentially a group under addition, so it's very good, very good.
Right.
I think that's the end of my question and then my remarks. I am very satisfied and very I'm very, very proud, I guess, of my friend giving this lecture. And I want to say one minor thing before we leave. Currently, the channel has 2 or 3 more contributors that is going to do lectures. The main problem is everyone here is a theorist. So me, Simba, and the other 2 people that are going to contribute are probably going to be theorists. I would like some people to talk about experimental work or computational work that they are doing. So if you are interested in this kind of polyphysics project, I encourage you to email me in the about section, and then we can talk, and then we can see if a talk giving a talk is viable. So thank you so much. Simba, do you have any final remarks?
No, I'm just want to remark that I'm sorry that I put the slides a bit
No,
off.
don't worry, la. Don't worry, la. It's all right. I mean,
Yeah, yeah.
you'll know. I mean, I don't want to say that I'm
Practice.
very
Right.
experienced. Like the more lectures you do, you'll realize that, oh, I did this something incorrectly. So it's a learning experience. Like everything in
Yeah,
life
right.
is a learning experience. Okay.
Yeah.
So no final remarks.
Yeah.
Okay. So thank you, and I hope you learned something. And see you in the next one. Bye bye.
Yes. See you.
See you. Let me see.